Welcome everyone. It is my very great pleasure to introduce Professor Robyn Owens, who is giving us this second plenary lecture at ANZIAM22. Professor Owens is Emeritus Professor at UWA and an elected Fellow of the Australian Academy of Sciences, the Australian Computer Society, and of the Academy of Technological Sciences and Engineering. Starting from her PhD in pure mathematics at Oxford University, Professor Owens built a distinguished career in research applying mathematics in the service of humanity and society, in the course of which she made many outstanding and prize-winning contributions, including winning the UK Rank Prize for contributions to nutrition in 2010, in recognition of her research on the use of computer vision for non-invasive measurement of human lactation. I'm sure we'll hear more about that in her talk. Professor Owens served as UWA's Deputy Vice-Chancellor for Research for 9 years until 2019. Less well known is the fact that Professor Owens served as my honours thesis supervisor and my first research mentor. She is my original role model for the application of mathematics to challenges in the world around us, for which I remain very grateful. I look forward to hearing from Professor Owens all about her brilliant, if apparently unpredictable, career now. Please join me in welcoming Professor Owens.
Thank you very much, Natasha, for that lovely introduction. And thank you, everybody, for listening to my talk on my unpredictable career. I'd like to begin just by acknowledging that I'm giving this talk on Whadjuk Noongar land and pay my respects to their elders. I'd also like to thank Matt Simpson and Michael Small for asking me to give this talk, and all the organisers for the conference. I can imagine that it hasn't been easy, a logistic nightmare perhaps, but it's running very smoothly at the moment, so thank you very much. I've found it very helpful. Okay, so I was asked to give a talk around my career, how it worked or didn't, and also some advice from I guess, the perspective of the sector at large, certainly here in Australia. So I've called my talk My Unpredictable Career, and it might be subtitled perhaps also as What is a Mathematician? And you'll see that as we go through. So let's start off. Here is the moment at which I suppose I got the first idea that I might actually do mathematics at university. And this was through the summer maths enrichment course that was held for school children or school students between years 11 and 12 to provide them with an idea of what maths at university might be like. And so many years ago, as you can tell from the fashion, but we were invited to spend 2 weeks in residence at the university to have a series of lectures in really quite abstract topics off the school curriculum and to see what life at university was like. And I have to say it was a wonderful experience for me, certainly changed my view of what mathematics could be like. It was a fabulous idea about being at university. And this cohort of people, while many of them didn't turn out to be mathematicians, they did turn into astronomers, lawyers, doctors, engineers. Indeed, if you look very closely, there is even an AFL football captain in that group. But moving on. So my first degree was at the University of Western Australia. And as I said, I studied mathematics. I enrolled in a fairly traditional science course, but in first year I fell in love with mathematics, and I would like to acknowledge my teachers here at the university. I had a fabulous set of teachers and really got to love mathematics as a subject. Interestingly though, when I told people that I was majoring in mathematics, the response was, so you're going to be a mathematician. And I had absolutely no idea what being a mathematician would mean. What was a mathematician? What did mathematicians do? The only mathematicians I could think of were all long dead, and I couldn't imagine what a career in mathematics would be like, even though I could imagine it in many other topics. Nevertheless, I wasn't worried about a job at that stage. I thought I would just get educated and do what I loved. So on from UWA, I was lucky enough to win a scholarship that took me to Oxford, where I did a master's and my doctorate, all in pure mathematics and all in an area of functional analysis. And interestingly enough, here again, the topic came up once more. In the tea rooms at the Mathematical Institute in Oxford, the graduate students would sit around and say, do you think we're mathematicians yet? What does it mean to be a mathematician? Well, at least I can read the papers, they would say. So maybe we were halfway there. Well, it was Charles Dickens, actually, who came up with the definition of a mathematician. He said a mathematician is a blind man in a dark room looking for a black cat that isn't there. And perhaps as a joke, it still seemed to summarize fairly well my PhD, because I was looking at a hypothesis that had been printed in the literature as to whether the Hardy space of functions that were analytic in the upper half plane and almost periodic on the real line was complete or not. And after 3 long years of research, I discovered it wasn't. So I have a fair amount of sympathy with Dickens' definition. But we'll come back to that later on, because after Oxford, I was then lucky enough to go to Paris for 3 years. And in Paris, I was working at the Université de Paris Sud, which is in Orsay, just outside of Paris in the south. And on the left there, you can see the Department of Mathematics, and on the right is just the entrance into the campus. So doing more mathematics, doing more pure mathematics, still having lots of fun, still wondering what on earth a mathematician might be. But my very first publication actually appeared in French in the Compte Rendu, and it was on the zeros of functions that are analytic and almost periodic, as you can see there. One might wonder why anybody would ever want to know about these things. It was very interesting, although I have to confess, not a terribly well-cited paper. After my time in France, when I was teaching as well, and actually in a department with very, very good mathematicians, I came back to Australia, joined the mathematics department at UWA, but quickly got involved in a very, very different kind of project. So going from the sublime to the ridiculous, I was involved in a project that was supported by the Australian Wool Corporation. This is back now in the 1980s, on robot sheep shearing. If there is a certain amount of mirth amongst the audience, fair enough. Everybody thought it was hilarious at the time too, whether it would ever be possible for a robot to shear sheep. Supported by the Wool Corporation, because at that time, the cost of shearing had soared tremendously. It was a very important part of the Australian economy, and the Wool Corporation looked at 2 possible projects for shearing sheep. One was a biological defleecing project, where you would feed the sheep certain chemicals that would cause the fleece to weaken, and then you'd essentially pluck the wool off the sheep. And the other one was this robot sheep shearing project that involved a robot shearing arm that you can probably see towards the top in the left-hand image. That's the sheep on another robot, the robot manipulator, and that robot would be able to turn the sheep over, and so we could get both sides of the sheep. Okay, how did it work? There was a sensor on the end of the shearing head, a capacitance sensor that was designed to measure the distance between the shearing head and the skin of the sheep. Now, normally human shearers are shearing blind. We actually had feedback in terms of capacitance measure, but nevertheless, we needed to know how to steer the shearing clips over the skin. And this is where my work came in. So I was working on a model for the underlying size and shape of the sheep's surface. It was a series of polynomial interpolations, and my job was to implement a Kalman filter in order to update that for any individual sheep. So prior to being sheared, the sheep were, a set of measurements were taken around things like weight and girth and length, etc. These predictors were fed into the Kalman model that would update the coefficients on the surface model in order to generate a surface that was closer to reality. And then the sensors on the end of the shearing head would moderate the adaptation of the robot to shearing. It seemed absolutely remarkable at the time, but it's really a reason why I can absolutely believe that robotic surgery will be much more accurate than human surgery, because the measurements were much more precise. And certainly with this work, we had far fewer accidents or nicks with the sheep than you would get with normal human shearing. As you can probably imagine, this was well advanced at the time, this work. Robots weren't doing anything more than general pick and place tasks. And it was right at the time when computer vision was first beginning to take off. But just before we go past robotics, many years later, I was able to visit the robotics lab at the University of Osaka, where here in this laboratory, they were busily trying to build robot babies with the capability of an 18-month-old child. And I can tell you those capabilities are absolutely enormous, and being able to get a mechanical device to respond in a way that a baby would is an astonishing amount of sensory feedback, adaptation, and an incredible amount of computer programming. So a lot of fun with robotics. But my early work in robotics actually got me to Berkeley. And I was invited to go and work at Berkeley for a while to give the inaugural robotics talk. Berkeley is a very interesting university. Interestingly, back to the topic of what is a mathematician, or indeed what do any academics do, the president at Berkeley once decided that he would like to know what all his academics did. So he instructed all the academics to keep a diary for a week so that he could find out what they actually did. And one of the mathematicians filled in her diary as follows: Monday, tried to prove theorem. Tuesday, tried to prove theorem. Wednesday, tried to prove theorem. Thursday, tried to prove theorem. Friday, theorem false. The story continues. What do mathematicians actually do? Well, while I was giving the inaugural lecture course in robotics, another researcher, Jitendra Malik from Stanford, had just been employed by Berkeley to give the inaugural lecture in computer vision. So he and I shared lectures, and this was exactly when computer vision was first starting to take off. So computer vision, what is computer vision? Computer vision is trying to get computers attached to cameras to understand the geometry and structure of the 3D world from the signal that falls onto the camera screen. And in order to interpret that in such a way that a person or a robot or another computer system could navigate in that scene. So here's a scene from New York, and the computer vision system is able to identify people and cars and traffic lights and buildings. And becoming, increasingly important as we try to develop driverless car technology and to have automated machines being able to navigate through the real world. So how do we do this? Very complicated. I can tell you that it's taken many years of research to get the technology to where it is today. And there's still a lot of research going on in this area. In fact, I have just finished working on the supervision team of a PhD student who's been working in the area of adversarial images. This is where signs in the real world, such as a stop sign or any other indicator, can be attacked with an adversarial image to trick a machine learning algorithm into seeing something other than what is actually there. So you could trick a driverless car into not being able to see a stop sign, even though the human would not be able to see that that image had been interfered with. So it's a very interesting field, if you like, of cybersecurity, still much to occur. But let's go right back to very early computer vision. And just for those of you who are not familiar with computer vision, and this is very simple, but just to give you an idea of what happens. On the camera screen, there is a series of grayscales, say, representing light intensity. So the image on the left is a highly pixelated image of a person. The image in the middle is the same image with the light intensity numbers in it ranging from 0 to 256, 0 being completely black, no light, 256 being. The image that you see is a low frequency image of a face that has been corrupted with some high frequency signals, that is the edges of the individual pixels, making it quite hard for you to see it. But if you were to blur your eyes a little bit, you will be able to filter out the high frequency signal and should be able to determine that this is an image of Abraham Lincoln. So, okay, so a signal has low and high frequency components. In order to understand what's in a signal, people first of all look for the edges in an image as a way of breaking up the image into its individual components. And so how do we find edges? Well, edges should be easy to find. They are where you have a peak in the first derivative or a zero crossing in the second derivative of the signal. So at the top, we have a one-dimensional signal, dark, light band in the middle, dark, or vice versa, and the derivatives underneath, you can see which way it's going. Okay, so to find that, we simply convolve the image with a first derivative convolution operator. I have a very simple derivative detector there, do a convolution, and you see the peaks there. Very simple. These ideas are used because, of course, psychophysicists and neuroscientists have actually found cells on the retina in the visual processing part of the human brain, in the visual cortex, that actually implement a number of mathematical functions, including simple convolution, derivatives, Fourier transforms, etc. It's absolutely remarkable that parts of pure mathematics that I thought were pure inventions of the brain are actually implemented in neural hardware. Okay, so you can do that to an image. There's an image of two guys in an office somewhere, and you can look for the derivative edges. Now, of course, it gets complicated depending on the scale that you want to do. So the image in the middle is a higher frequency image. You can see a lot more detail, for example, in the front chap's tie than in the image on the right, where you've just looked for a much lower frequency edge detector. And of course, the trouble with taking derivatives is derivatives are essentially noise enhancers. So you've got to deal with the whole problem of noise. The more edges that you want, the more noise you've got to deal with. And so what people do there, of course, is implement Gaussian smoothing. So here's Gaussian smoothing implemented as a convolution with a Gaussian approximator. The brain actually has neural components to do this as well. So there's an image on the left, and the image on the right, you can see, is the Gaussian filtered image, slightly blurrier, but all the texture on the grass, for example, has fairly much disappeared, and nobody really cares about where the edges of the grass fronds are. You're looking for the more important low frequency edges. Okay, so you take a Gaussian. Now we want to differentiate it. Rather than looking for peaks, we'll look for zero crossings of the second derivative. So now we have the Laplacian of a Gaussian. That curve is illustrated on the right-hand side. And to neuroscientists, this particular filter is known as the Mexican hat filter, and exists in neuroscience. So the brain can do Mexican hat filtering or the Laplacian of a Gaussian filtering. There are some filters to represent the Laplacian of a Gaussian at various scales. You compute the zero crossings and you can get the edge detection done. So this form of edge detection was very common throughout the 1980s, and an Australian researcher working at MIT, John Canny, actually did the definitive work on the differentiator as an edge detector, worked out the optimal edge detector, and the Canny detector was thus born. Okay, it can get complicated, but very interesting work. But there's another way of doing it. So this is some of the work that I was involved in. So instead of looking to the derivative as a way of determining where the edges of an object are, we took a completely different approach to say, how would a step edge be built up? So let's look at the image on the left-hand side, where I have a set of sine waves that are being added up to eventually converge to a step edge that would be dark on the left-hand side and light on the right-hand side. So there is sine x minus a third sine 3x plus a fifth sine 5x minus a seventh sine blah, 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 add it to infinity, and you get a step edge. Likewise, you can do it for a peak edge. There's a series of cosines there that add to a peak wavefront. The thing to note, though, in building up a step edge out of a series of sine waves is that all of the sine waves are in phase at the point where the edge occurs. And this was our big clue as to how we might be able to build another edge detector. The work started out because I was actually working with a series of psychophysicists on a very classic optical illusion known as Mach bands. So in the image on the left-hand side, you can see a waveform that starts off as a dark band on the left-hand side. Then there is a ramp upwards to a grayscale band, a further ramp upwards, and then a white band on the right. If you look carefully, and I hope you can all see this, at the points of derivative discontinuity, that is at the edge of the dark band turning into the ramp turning into the grey band, etc., you can see artifacts that are stripes. For example, if you can follow my cursor here, you should be able to see something that looks like a much brighter white band than anticipated. Likewise here, likewise a dark band there and a dark band there. Mach bands had been known for quite a while. They were first observed by Ernst Mach at the edge of shadows, and they're well known in the medical community because they appear in X-rays as artifacts that are not actually in the underlying signal, and radiographers have to take this into account when determining how to interpret an image. So if you think back to, let me just flick back one slide, if you think back to how the step edge is being made up, you see that as you're adding up a series of sine waves, and here's the first umpteen added up, you see, you see that you get this overshoot on one side and an undershoot at the other. That led to, well, first of all, led to a paper in Nature describing how Mach bands can be interpreted, and led on to a new form of edge detection known as feature detection, edges or peaks or many other things from local energy. Because by taking a signal and its Hilbert transform, a 90-degree phase shift of that signal, we were able to compute what is known as a local energy function, and the peaks of that local energy function occur exactly where you have this phase congruency occurring. This particular feature detection algorithm really took off and led to a whole pile of new methods for edge detection, and was implemented in wavelet technology and is now used in many systems all over the world. Okay, so I'd like to, by this stage, I should warn you that I'm not working in a maths department anymore. I actually had a job in a computer science department. I was teaching robotics, I was teaching computer vision. and various other parts of the computing curriculum. And my work was becoming more applied, if you like, or certainly less in pure mathematics. So I'd just like to go over a couple of other projects that I worked on. One was an application in sign language understanding. So here we have my colleague here, John Holden, who was my PhD student, subsequent postdoc. And we worked on the problem of seeing if we could get a computer to understand Australian Sign Language, Auslan. In order to do that, we had to be able to track a face, a hand, lip movements, and decode those signals into a language, in fact, decode them into English. And if you can see the little avatar up in the top right-hand corner, I can't because my videos are over the top of it, but anyhow, if you can see that, that was a little avatar we built. That was the inverse problem of taking in an English sentence and turning it into an avatar that could sign. So what sorts of things did this use? Well, lots of image processing techniques, certainly including feature detection, edge detection, modeling, etc. But tracing lip movement and tracing individual finger movement, we used a technique called Bezier curves and spline interpolation, where you could measure individual features on a face or a hand, like the edges of lips or the components around the edges of a finger. And then as that has been moving, you could trace the movement of the spline as well. Okay, moving on to something else. There's a lot of work that was undertaken in the area of shape from structured light. So the way we perceive the world involves a projection of the 3D world onto a two-dimensional screen. And effectively, it should be uncomputable, except that we have a lot of constraints that make it computable. And so we can get a lot of shape from a number of different signals. There's shape from texture, shape from shading, shape from stereo, etc. Structured light is a process where you project light onto the screen in various structures and you use the deformation of those structures, those structured light shapes, to work out what the underlying geometry should be. It's not passive vision, it's active vision, very similar to echolocation used by bats and dolphins. So you have a stripe projector. At one point, it projects a stripe onto an object. You have the image of that stripe that's collected by the camera, and you try and work out what the underlying shape is. We were using this project in a collaboration with a professor of biochemistry, Professor Peter Hartmann, to try and understand human lactation. So here we have a sequence of binary light patterns that are shone onto a human breast. So starting out with very coarse scale binary patterns and becoming increasingly finer. The idea of using a set of shape patterns means that any individual point on the underlying object has a binary code attached to it, depending on whether that stripe is on or off, so that when stripes show a discontinuity, you can determine which stripes belong to which part of the body. This work was then able to measure not only the general shape and size of a lactating breast, but the change in size as the breast was producing more milk, and then subsequently the physiological components that controlled the structure and production of milk. Many things were learnt, and as Natasha mentioned, this went on to win an international prize, actually, that's given out by the Royal College of Physicians in the UK. It's the UK Rank Prize, produced by Lord Rank, whose family owned mills in England, also the same Lord Rank that ended up founding Rank Xerox. They award 2 prizes each year, one for research in nutrition and the other in optical electronics. We're probably the only winners who probably spanned both forms. We won in the section for nutrition, and this is Professor Peter Hartmann here with me receiving the award. Okay, just finally, some other work that I worked on with the postdoc is in face recognition. So many systems in face recognition detect points of interest on the face. edges of lips, nose, eyes, etc., but using 3D imaging structures such as laser or hyperspectral imaging or stereo imaging, you can compute the underlying shape of a face, and there you can then produce little patches of surface and look for changes in the curvature of those patterns to produce the underlying shape of the face, so that while people may be able to put on masks or put on sunglasses or put on makeup or change their hair, etc., it's pretty hard to change the underlying differential structure of a face. So I did this work with the chap whose image is down the bottom, Ajmal Mian, a PhD student, postdoc, now a future fellow at the University of Western Australia. It really resulted in state-of-the-art feature detection. We use this all the time whenever we come in and out of the country, or at least whenever we were able to do that in the past, because it's part of the system in our passport recognition. And all of you who have got your MyGov ID and had that verified through their system, that's also used structured light in order to match your face images with the underlying databases that the government has through things like passports or driver's licenses. Okay, that resulted in a paper that's been fairly highly cited, which is basically state-of-the-art in automatic face recognition. Okay, all this work was done while I was in computer science. So when I came back from France, I started off in a maths department with short-term contracts. I had postdoc contract working on the sheep shearing work. I then managed to get a continuing academic contract in the School of Computer Science, went through various levels of promotion, had a wonderful set of PhD students to work with, became head of school, and after that moved on to Dean of Postgraduate Research and then eventually Deputy Vice Chancellor Research. And I want to talk about those two things a little bit, because that was really when I probably started doing less technical work and more systems level work. And I think where my training in how to think like a mathematician really helped analyze problems. Okay, so at the time I was Dean of the GRS, there was a big project going on in the United States by the Carnegie Institute on what was happening with PhDs. So what was the problem? Well, the problems were that PhDs were taking too long, and in the States, and particularly in the humanities, up to 10 years, but even in the sciences, 5, 6, 7 years was not unusual. There are more and more students doing PhDs, and there were fewer and fewer being employed as academics. And during this time, during the last few years, I also did another project with ACOLA, the Australian Academy of Learned, Australian Society of Learned Academies, and on exactly the same thing. And it's the same data in Australia as well. At the time that we did it, which was about maybe 3 or 4 years ago, at any one time, Australia is training 80,000 PhD students, graduating 10,000 PhD students a year, and fewer than 10% of those graduates will end up as tenured academics. So are we doing the best job, and what are we doing it for, really? So the Carnegie report came up with what they thought graduates of a discipline, PhD graduates, should be able to do. They should be able to conserve, curate, and communicate their discipline. Indeed, in many countries, this broad knowledge of your discipline, certainly in the States and much of continental Europe, is part of the PhD training, and it's why we give our graduate students the opportunity to teach, to be able to conserve, curate, and communicate the discipline. Of course, to be able to add new knowledge to your discipline, that's what PhD training is about. And thirdly, to be able to apply the methods from your discipline to solve problems in other disciplines. Obviously, something that applied mathematicians are very good at, or should be very good at, and which I think is critically important, well, in all disciplines actually at the moment, but particularly mathematics. So I just wanted to finish off with this slide and a little bit of a discussion, which I've called Existential Topics, really. So why I think it's really important for us to address the question of what is a mathematician. And, you know, I could have asked you, can you give me the necessary and sufficient conditions that would define a mathematician? But I rather suspect that would be extremely difficult. I think that if we make it too tight, we would exclude people that we want in it. And if we make it too broad, we might include people that we don't really think are mathematicians. I don't know. I'm very open to this as a discussion, but I think identity is really important. And I see some disciplines in the sector that have a very strong sense of identity. Let's take as an example, for example, the astronomers in Australia know each other, work very well together, but more than that, they write decadal plans of what they're going to work on and they stick to it. They have an idea of how to push their discipline forward in a global context where Australia can best contribute. And that is a very powerful tool in order to gain resources, and the resources that you need in astronomy are very expensive, but they're very successful in getting a lot of resources to support it. The second reason I think it's really important, and I know we have a keynote on this on Thursday, is the rise of data science. So data science is something that I guess maybe we all took for granted in some way or other, but it's definitely created an identity recently. And now I suspect that most universities in Australia, and indeed even in the world, have data science recognised in some way or other. Maybe not as a department of data science, but probably as an institute or a research centre, certainly people appointed as professors of data science. And just in the last year, the Australian Academy of Science wrote a paper on the need for Australia to recognise data science as a discipline, which I think is very interesting because previously nobody would have thought of it as a discipline, but rather as a multidisciplinary approach to solving problems. To recognise it as a discipline means the rise of data science journals, but it also means a call for an FOR code and for ERA evaluation. And that's all tied up with identity, and it's all tied up with access to resources. So I think this is just hugely important for the mathematics community and computer science, but the mathematics community in particular, to address this rise of data science as a discipline, and whether maths is going to be part of it or going to be threatened by it. The most recent thing, of course, is the push for industry relevance. And I'd just like to mention this because we think of our undergraduate training as generating graduates who can think like mathematicians. And certainly the PhD training is generating well-formed individual researchers who can add knowledge to the discipline. Generally, in most other disciplines, the master's level is the level where you train graduates who could work as mathematicians. And to work as mathematicians, we have to know what it means to be a mathematician and what people can work as if they're working as mathematicians. And I think in order to do that, we maybe need to think of the idea of having more than one label on ourselves. So instead of just being a mathematician, you can be a mathematician and a biologist, or a mathematician and an engineer. Indeed, you know, in thinking about mathematicians and who might fall into a definition of who is one or not, we would all, I think, agree that Évariste Galois was a mathematician, even though he died at the age of 20, probably never worked in a university, was never paid to be a mathematician. His Wikipedia entry says he was a mathematician and a political activist. He certainly had two titles. So I think it would give students a better sense of what they could do as a profession if they're not going to be academics, tenured academics. What does it mean to be a mathematician and work as a mathematician? And how do we reshape our master's training in mathematics to do the formation of that individual who is industry ready to be a mathematician without being a university academic? And I think all this is just essential for the sustainability of mathematics as other areas arise. And with that, that's the end of my talk. Thank you very much.
Okay, thank you so much, Robyn. That was fascinating, and I'm not sure if we have any means of communicating applause, but maybe I'll invite everybody to knock the desk or applause to thank you very much.
Thank you.
Okay, we're seeing some applauses coming through on the chat now. Okay, so I see that Graham Hocking, hello Graham, has raised his hand. Graham, can you type a question into the question and answer screen? I've got one question. We do have a few minutes for questions, not very many, but a few. So from Michael Small, Michael asks, given, as you said, the critical thinking, problem-solving skills acquired through a mathematics PhD served you so well in your executive roles, he asks, why are there so few mathematicians in leadership positions in Australian universities?
Yeah, that's a really good question, actually, and I don't know why, although I might address this a little bit on the WMSIG panel tomorrow, and that is that, well, maybe it takes a certain amount of courage to, move out of your own little tribe and to start engaging with other people, and it certainly, it takes a sense of having a little bit of social capital as well. But look, I have enjoyed immensely using what I consider to be the discipline of analytic thinking, getting my terms well defined and correct, getting the data relevant to the problem that you're trying to solve, using logical thinking to try and solve problems has been enormously helpful. And I think that university leadership could well and truly use the skills that mathematical education develops to address many of the problems that we have today.
Okay, that's very interesting answer. I'm not seeing any other questions. There's lots of enthusiasm and gratitude for a really interesting and exciting talk. So just generally, if anybody would like to ask a question, if you could try to type your question into the Q&A box, that would be great. In the meanwhile, Robyn, if you don't mind, I might go back and ask a really low-level computer vision technical question. So my question is there any dependence in the results of the analysis on the use of the rectangular grid? Are there other forms of grid, and does it make a difference to what kinds of features you can detect or the orientation of those features?
I think mathematically it's a really interesting problem, actually, and there's been quite a lot of work on the topology of grids. And indeed, you'll see in various insect vision systems that their eyes and the topology is different. For example, a hexagonal topology gives different topological properties, particularly with regard to continuity, that you don't get just with a square grid. But a square grid, of course, is immensely simple. And with the power of modern computing, you can move to extremely high resolution, so that the sort of problems that were originally a problem when it was just at the beginning of computer vision, it's sort of just gone away with the sledgehammer approach to computational power. But I know that there's another plenary later this week that will be very interesting also on the fundamental biology of computer vision and human or biological vision. And, my own personal opinion is I really think this is going to be the century of biological mathematics. There's just going to be a huge amount of interesting work done.
Okay, so we do have, thank you so much. It is an interesting answer, which I hadn't necessarily expected. So there's a couple of questions that are slightly related for you. One is, do you think mathematics departments need to change? And if so, how? And then the other question, which I'll join together with that, is what do you think needs to happen in a graduate education for a mathematician to make them industry ready? So how do you get graduates of mathematics industry ready, and do mathematics departments need to change?
Well, I wouldn't want to speak for all mathematics departments, and I probably wouldn't even want to speak for the maths department at UWA since I haven't been in it for decades. But my feeling is that if I were to think of two changes I would recommend, one is a little bit more outward looking. you know, going and talking to people in other disciplines and finding out what their problems are. Because, you know, just gazing at your, and I'm not suggesting anyone's doing this, but just gazing at your own belly button for decades is not doing mathematics a lot of good. It's going to be stimulated by hard problems out there that mathematics might not have the answer to now, and it may be new mathematics that's needed to develop it. But after all, mathematics is the language of the universe. And, you know, if we don't have the words or the grammatical structures for the problems at the moment, then it's up to mathematicians to go and develop them. What was the second question? The second question was about training. I really think that we should think about this, actually, because, you know, if you think about some of the professions like engineering or medicine or law, they actually take their master's training level as the professional training level. So they have a sense of where the target jobs are. And, you know, look, let's face it, you know, engineering's got millions of jobs. You could be a bioengineer, a medical engineer, or electrical engineer, or a civil, or whatever. There's a lot of variety there, but they do have a sense of jobs. And I think what they do in continental Europe is this notion of formation, you know, where you have a lot more engagement with your potential industry and mentorship. There's individual mentorship to get you from your skill set into the workplace. I think that would be really important. I suppose I started with a quote from Charles Dickens. I might finish with one from Charles Darwin, who said, "It's not the strongest that are going to survive, nor is it the most intelligent. It's those most able to adapt to change." And I think, you know, I think that's the challenge to maths departments, to look at the outside world, see how it's changing. And not just maths departments, of course, though. Don't think I'm attacking maths departments here, probably universities in general. But we have to look at the outside world and be able to adapt. And, you know, the thing about data science is if we don't adapt, it'll take over.
Okay, yeah. I think that's, oh, sorry, you have one more, we have a minute, Robyn.
Well, you know, I'm not going to criticize data scientists at all. I'm sure they do a lot of great work, but, you know, increasingly data science these days is done immensely through machine learning. And what's the biggest problem in machine learning is explainability. It's just a black box. So, you know, if you're going to look at the difference between a mathematician, a blind mathematician in a dark room looking for a black cat that's not there, and a data scientist doing the same problem, at least the mathematician knows why the cat isn't there. My take.
Okay. That's been a lot of fun. Thank you so much, Robyn. I think to keep on schedule, I can see the audience is thanking you like crazy, lots of applause coming through. So thank you very much. And I will declare this webinar ended and ask Fiammi to end the meeting. So thank you again so much for a fascinating talk.
Thanks, Natasha.